Hey guys, if you remember from before break, we were discussing exponents, properties of exponents, exponential equations, and graphs of exponential growth and exponential decay. What we're going to do next is connect those to logarithms. And the point of a logarithm is for us to be able to solve for an exponent. Just for as a quick example, if I gave you 2 to the x equals 8, hopefully you'd recognize that as 2 to what power is 8, and you happen to know that x equals 3 in that case. And if I said 2 to the x equals 4, you would know that the answer for x is 2. But what if 2 to the x equals 6? Well, we don't know what that is. The best that we could say is that our answer for x is between 2 and 3. Because we know if it's 2, we should get 4, which is less than 6. And if it's 3, we should get 8, which is more than 6. So in between 2 and 3 is as good as we could do until we start talking about logarithms. And so if I have some expression b to the x equals a, that's our exponential form, the equivalent logarithmic statement is going to be log base b of a equals x. So what that allowed us to do was to solve for this exponent here. I got x by itself if we write it in terms of a log. And so while maybe conceptually the idea of a logarithm is a bit abstract and can be difficult, really I think the biggest thing that can help you understand them is to be really good at exponents and properties of exponents, because the properties for logarithms that exist are all the same as the properties that exist for exponents. They're really the same thing. So try and keep that in mind as we're doing this, because you can always write some sort of exponential statement as a logarithm. So write each of these exponential statements as the equivalent logarithm. And so this is b to the x equals a, if you want to use our example that we have over here. So that's going to be log, oh, son of a gun, let's try that again. Log base 1.2 of m equals 3. Now, another way of thinking about this, and it's not by any means, elegant or anything. Let me move this up here. That's our answer. But if I have 1.2 cubed equals m, which is an exponential statement because it has an exponent in it, and I'm asked to write it as a logarithm, kind of the cut and paste brute force method is, if I just write the word log out in front of the exponent, and then I switch the exponent with the constant on the other side. So I wrote the word log out here, and I'm going to switch the 3 and the m, the exponent with the constant on the other side. I end up with log 1.2 m equals 3. That's another way of thinking about it. That 1.2 becomes the base of the log. It's not on the same level. So it's on the log is log base 1.2 of m. So the argument of the log is m. 1.2 is the base. But if you're looking for just kind of what mechanically am I doing here, you're just writing the word log in front and switching the exponent with the constant on the other side. So with that same reasoning, I'm going to write the word log. It's going to be base e, and I'm going to switch the 9 with the b. Another way to write this would be natural log 9 of b. And again, this is the argument of the log. This notation ln is log base e. Log base e is equivalent to natural log. And then log base a of 24 equals 4. All right, and anything we're able to do one way, we want to go ahead and do it backwards. So going from logarithmic form to exponential, and that, for example, is going to be a to the 5th equals 4. And I'm just using my equivalency statement from up here. But another way of thinking about it is undo what you did in the previous one. Kind of, again, mechanically speaking, if I have log base a of 4 equals 5, if I want to turn this into exponential, I'm going to get rid of the word log, and I'm going to switch these guys back. And if I do that, I end up with a to the 5th equals 4. So get rid of the word log and switch the argument of the log with the constant on the other side. E to the negative 3 equals b. Again, switch those guys. And then lastly, 3 to the c equals 5. So that's just going back and forth between exponential and logarithmic form. We'll talk more about what exactly is happening when we do that, but for now, if you know the operation to get from one to the other, you're in a good spot. We'll start with some values that we ought to be able to figure out. Find the exact value of log base 2 of 16. So this is log base 2 of 16. That's how that's read. Remember, this is the argument of the log. What it's really saying is 2 to what power is 16? That's what that question's asking. And when you think of it that way, 2 to what power is 16? Then that's going to be equals 4. You could go through the exercise of saying, okay, log base 2 of 16 equals x, equals something. I get rid of the word log, and I switch those two guys. 2 to the x equals 16. Oh, well, I know that. 2 to the x equals, this is 2 to the 4th, and then we have equivalent powers there. By the same logic, this question is saying 3 to what power is 1/27th? Now, you may not know that immediately off the top of your head, but 27 in terms of powers of 3 is actually very useful, because 3 squared is 9, 3 cubed is 27. So if it were log base 3 of 27, we'd say 3 to what power is 27? Well, that's 3. But it's the reciprocal of 27, 1 over 27. So this is 3 to the negative 3rd is equal to 1 over 27. So the answer to 3 to what power is 1 over 27? The answer is negative 3. The domain of a logarithmic function, when it comes to exponentials, right, you can plug in pretty much whatever you want as an exponent of a value, but we do run into a problem, though, with the logarithms, the restriction on the domain. Again, if you remember exponentials, they tend to look like this. So no restriction on the domain, goes left forever, goes right forever. But remember that the argument of the log, this is saying 2 to what power is x plus 3. The argument of the log, this right here, has to be greater than 0. And the reason that that's true is because if I have y equals log base 2 of x plus 3, let's say 2 to the y equals x plus 3. 2 to the y, this is a y, by the way. I can plug in whatever I want for y. That's fine. I could plug in 1,000. I could plug in 0 for y if I wanted to. I could plug in negative 10. But as I plug in larger and larger values, hopefully you see that that gets larger and larger. If I plug in smaller and smaller values of y, when I plug in y as 0, this just becomes 1, right? If that's 0, 2 to the 0 is 1. If I plug in, let's say, negative 10, that's equal to 1 over 2 to the 10th. Now, 1 over 2 to the 10th is a very, very small number. But what is it not? It's not 0. So there is no way to make this 0. Therefore, I can't have this be 0. The argument of the log has to be greater than 0. That's the restriction. So all that said, x plus 3 has to be greater than 0. And it can't be 0. It has to be greater than 0. So x is greater than negative 3. And that's true for all these log statements. B here, 1 plus x over 1 minus x has to be greater than 0. Here, absolute value of x has to be greater than 0. If we go back to B, 1 plus x over 1 minus x is greater than 0. If there's a restriction on x here, let's see, if I multiply the 1 minus x over, then that's going to go away. I get 1 plus x is greater than 0. So x is greater than negative 1. I can check that back here. Let's see. It's like I also have a problem at 0, or excuse me, where x is 1. So multiplying this over and losing that term is a problem. If you remember back to these rational functions and rational inequalities, we had to look for, quote, x-intercepts, things that made the numerator 0, and things that made the denominator 0. So really, I've got a problem here at negative 1, as we saw, but also at 1, right? 1 minus, if I plug in a 1, I've got like an asymptotic issue there. So if these are my critical values, I need to test where this is good and where it's not good. So if I test, let's see, what did I just say? Was greater than negative 1. I think that was what I said. So negative 2, is that going to work? Let's try negative 2. 1 minus 2 over 1 plus 2 is negative over positive. That didn't work. No good there. If we tried 0, we know 0 worked because that ended up being 1 over 1. And that was greater than 0. So that worked out. And if I try 2, for example, make sure we're okay there. 1 plus 2 over 1 minus 2, which is 3 over negative 1. Ugh, so I've got a problem there. So only between negative 1 and 1 are the values of x that are going to mean that this thing exists, because I can't have the argument of the log be negative. So 2 is out of the question. It's got to be between negative 1 and 1. And let's see, this one, 1 itself was exclusive. Negative 1, I believe, was inclusive. There we go. And then the absolute value of x being greater than 0, that's always going to be true, right? So in this problem, x is all real numbers. Oops. Right, because even if I plug in a negative value of x, the absolute value part is going to turn out to be positive. So I'm looking good there. So what does that mean for the graphs of the logarithmic functions and its inverse? Well, its inverse is the exponential. That's the relationship between the exponentials and the logarithms, so that they're inverses of each other. So here we have f of x equals 3 log x minus 1, this being the argument of the log. And remember, when there's no log, when there's no log written, there's a base 10 assumed there. So log base 10 of x minus 1. So as far as the domain goes, the domain, x minus 1 needs to be greater than 0. Therefore, x is greater than 1. So, right here, I know I'm only going to have a graph to the right of 1 there. And part B, let's graph it. Okay. Maybe we'll plug in some values that we like. So it's got to be greater than 1. So things, I could plug in 2. But let's think about that for a minute. If I plug in 2, I get log base 10 of 1. 3 log base 10. If I plug in 2, I get 1 there, which is asking 10 to what power is 1? Well, actually, I happen to know that. 10 to what power is 1? Well, that's 0. So just this part is equal to 0. 3 times 0 is 0. So that point right there, that exists. If I were to try and plug in 3, though, 3 log base 10 of 2. Now I've got problems. I can't do that without a calculator. Because 10 to what power is 2? I have no idea. So maybe we should pick something that I do know. Wouldn't it be great if I had, say, log base 10 of 10? Because all of a sudden, that's saying 10 to what power is 10. I happen to know that that's 1. So what value of x makes the argument 10? Well, 11 does that for me. If I plug in 11, 11 minus 1 is 10. 10 to what power is 10? Well, that's 1. And I get 3. 3 times 1. So I have to go off the page here. 1, 2, 3. So I get that point right there. 11 and 3. And a picture looks like that. As far as plugging in a value going the other way, it's going to get smaller and smaller. You would want, for example, 3 log base 10 of 1/10 would be the next thing that makes sense, because just looking at the logarithm part, the answer to that is -1. 10 to what power is 1/10? That's -1. But what value do you have to plug in? What minus 1 gets you 1/10? It's actually 11/10. And that's going to get you -3, something like that. It's not worth really executing that, because you're not going to be able to plug anything less than 0 in there, and this is going right. You're never going to get to 0 here. I guess you're never going to get to 1 is what I should say, because we can't plug in a 1 there. But this is going to negative infinity for sure. So as it turns out, this red line here, 1, is a vertical asymptote. X equals 1. It's my vertical asymptote. Find the inverse. Okay, so that means I got to switch. X equals 3 log base 10 of y minus 1. So that's x over 3 equals log base 10 of y minus 1. And I'm going to now write it in exponential form, get rid of the log. 10 to the x over 3 equals y minus 1. And then y equals 10 to the 1/3 x, or x over 3. And then what do I do? Plus 1. There we go. So not the neatest thing I've ever done in my life. Let's try that again. 10 to the x over 3 plus 1. And this is y inverse, or f inverse of x. So, based on what we know, we have something raised to the x power. It's exponential, and it's going to be growth. So that base is 10, and shifted up 1 unit. So we have a horizontal asymptote there at 1, and I could plug in some values. Let's see, a value here that would make sense just to make my life easy. If I plug in a 3, maybe that's good, because then I get 10 to the first power. If I plug a 3 in there, 10 to the first power is 10. 10 plus 1 is 11. Okay, well, 3, 11. So 1, 2, 3, 11 is right there. Some other point that I could plug in. I can plug in 0, can't I? I could plug in 10 to the 0 over 3, which is 10 to the 0. And then that's 1. 1 plus 1 is 2. So 0, 2, it goes through there. And this is exponential growth, so it's going to look like this. There we go. And really I should have done all this in another color. Let's try that. A little more deliberate here. Just I want the red graph to go with the red asymptote and the blue graph to go with the blue asymptote, just so you don't get confused. There we go. There's the graph of f inverse. The domain and range of f inverse, well, we know that the domain of the inverse is all reals. The range is greater than 1. And we graphed f inverse there. So let me throw E in there. The domain is all reals, and the range is y is greater than 1. So what you notice is hopefully that these are in fact inverses. If I graph the line y equals x, that's pretty close. They're mirror images of each other about that line. Just turn your head 45 degrees. And the points that exist, 2, 0, and 11, 3, are now 0, 2, and 3, 11. Well, the points have been switched. That's the relationship that exists. And so the last bit here, and we'll likely talk more about this next class, is solving log equations. And if they're not solvable, we'll talk about them next class. If they are solvable, then we can do them. But we got to get this x by itself. So go from maybe logarithmic form to exponential. So that's going to be 3 squared equals 4x minus 7. So 9, add the 7 equals 4x. So that's what, 16, and I divide it by the 4 equals x. So x looks like it equals 4 there. over here, x squared equals 64. We could take the square root of both sides, and we get calculably plus or minus 8. But as the log base, 8 and negative 8 to what power? I think we're just going to have just the positive one there. I don't think we want a negative log base. And then this is where we're going to run into problems, and we'll just leave it in logarithmic form because we have an exponential here that we need to solve. So if I want to get rid of this e here, I'm going to take the log, or I'm going to write the word log out in front. E5 equals 2x. Therefore, x equals log base e of 5 over 2. And again, another way of writing that is natural log of 5 over 2 equals x. And for now, there's your exact answer. We'll talk about how to get maybe a decimal on the calculator and what to do with that next class. But you should be on your way solving logarithmic equations using exponents, solving exponential equations using logarithms, the graphs of exponentials and logarithms and how they're related. Remember that the domain of the log function, the argument has to be greater than 0. I took all these arguments and set them greater than 0. And that the log is asking the question, 2 to what power is 16? Right, so 2 to the x equals 16 there. And don't forget this guy, this conversion, and how to get from one to the other. So we'll talk more about this in class, but now you've got a set of notes on a video to refer back to. Enjoy.